Alright, we're starting the Chapter 6 homework review right as the exam that covers this topic is about to start. So let's get right into it. The average this week was 8.86 out of 12, which is a little bit lower than the last time I taught this course, but not alarmingly so. And I think one of the things with Chapter 6, as you found, is that there's a lot of different topics. So we covered all aspects of aqueous reactions, which included molarity, 3 categories of aqueous reactions, stoichiometry, so just a lot of different things going on to keep straight, none of them being particularly in-depth or difficult, just a lot of things to bring forward. So that said, despite there being a lot of topics, I think there was only a few that seemed to give us widespread trouble on this assignment. Problems dealing with molarity and a little bit with acid-base reactions and redox reactions seemed to be the ones that gave us the most trouble, but in general we did pretty well on most things. So let's get right into it with the problems that I've identified. A couple of these were requests from students, and the rest of them are going to be ones that I identified based on the results in Blackboard. So the first few problems deal with molarity, and there's different flavors of this calculating molarity, and it's fairly important because it does relate a lot to stoichiometry in solution as well. So the first one is a pretty straightforward one. It just asks us to calculate the molarity of a solution prepared by dissolving 1.495 moles of lithium hydroxide in enough water to give a final volume of 750 milliliters. So whenever we're calculating molarity or using molarity in any context where we have to calculate it, remember we have to define it. So molarity, capital M, is moles of solute, so that's whatever is going to be dissolved in the solution, divided by the volume of the solution, but in liters. So specifically, it has to be liters in the denominator for this to work. So those are the two things we divide when we're calculating molarity, and the moles part is going to be either more or less straightforwardly given to you, or you have to calculate it yourself. In this case, it is given to us. So here we're looking for the molarity of lithium hydroxide. That's the substance we're dissolving, so it's just going to be the moles of that substance divided by the liters of solution. I guess it's more appropriate to say liters of solution, not in solution. Okay, so again, the volume of the solution is mostly water. I mean, we're dissolving things in water in this context, and so the volume of the solution is going to mainly be the water that's dissolved in, plus the substance that is dissolved in there, but it's all single phase, so you can't distinguish them. But those are the two quantities we need to calculate it. So in this problem, moles is given to us directly, so it's just 1.495. We don't have to do any calculations for that. And then the liters of solution, we have 750 milliliters. So that's the volume in milliliters, and we have to divide by 1,000 to get 2 liters. So that you should become good at doing even in your head, because we need to convert between milliliters and liters often in this part of the course. So it comes out to 0.750. So that's going to go in the denominator here. And I think this comes out to 1.99. Let me double check that. Yeah, so this comes out to 1.99 molar. I don't know if this is multiple choice or numerical, but whatever the case is, this is the answer that you would put in to Blackboard, 1.99. Okay, so that's how we calculate molarity, in this case, as straightforward as it comes, because you were just given the number of moles. Now, in the rest of these, we have to figure out the number of moles that we're looking for. So in this case, we're actually not going to be calculating molarity, we're going to be using molarity as a conversion factor to relate to something dealing with moles. So a 0.150 molar sodium chloride solution is referred to as a physiological saline solution because it has the same concentration of salts as a normal human blood. Calculate the mass of NaCl solute needed to prepare 275 milliliters of a physiological saline solution. So again, in this case, we're given the molarity, so we're not calculating it, but we're still going to use that definition of molarity to help us do this conversion. So we want to prepare 275 milliliters of this solution. We want the concentration to be 0.150 molar, so those are the two essential numbers, buried in all of this unnecessary background. So those are the numbers we're dealing with, and what we're looking for is the mass of sodium chloride. So that's kind of what we're trying to calculate here. Alright, so we don't specify the units, but if it was multiple choice, it would be given, and probably most, in any case, it'd be in grams. So we're looking for the grams of sodium chloride needed to prepare 275 milliliters of this solution. So we have everything we need to do the conversions. We're going to start with the volume that we're looking for, and then use the molarity as a conversion factor. So we're trying to make 275.0 milliliters of NaCl solution. And then we want to figure out the mass of that, so we're going to use molarity as a conversion factor to figure out how many moles of sodium chloride are in there. So 0.150 molar means we have that many moles per liter, or 1,000 milliliters as I often do it. Alright, so we want milliliters to cancel out. So this molarity tells us that we have 0.150 moles of sodium chloride per 1,000 milliliters of the solution. So that allows us to calculate moles of NaCl. This is a step that we use a lot in solution stoichiometry problems, volume and molarity, to calculate moles. And then from there, we just have to go into grams. So we've talked about in chapter 5 ad nauseum how to calculate grams for moles or vice versa. So we're going to use the molar mass of sodium chloride, which is 58.44. We have to calculate that. But 58.44 grams per mole is the molar mass of sodium chloride. So there's 58.44 grams of sodium chloride in 1 mole. So that allows us to cancel moles and calculate grams, which is what we're going to end up with in this problem. So we have 275 milliliters, 0.15 molar, and that comes out to 2.41 grams. Alright, so if we dissolve 2.41 grams of sodium chloride in 275 milliliters, that's going to give us 8.15 molar solution. Let me double check the numbers. That sounds a little high, but maybe that's right. Yeah, it should be right. Okay, so that's going to be a problem where we're not calculating molarity, but we're using molarity as part of a conversion. And so molarity being a compound unit, moles per liter or moles per 1,000 milliliters, as I wrote it here, that's a way to convert between volumes and number of moles. Alright, then we just have two other problems that deal with, or 2 or 3 other problems that deal with calculating molarity or moles in solution. And these ones, in some cases, are going to deal with mixtures of things in solutions, or calculating the molarity of a specific thing in a solution that has more than one ion dissolved. So here we say a solution has 12.7 grams of sodium carbonate in 1.28 liters. What is its sodium ion concentration in moles per liter? So here we're looking for the molarity of sodium plus. So what we have to keep in mind is that when we dissolve an ionic compound or an acid in water, we're going to separate ions. We talked about that in the context of strong electrolytes. You dissolve something like that in water, and ions separate, positive ions, negative ions, sort of falling apart and being surrounded by water and pulled away from each other. But when we calculate molarity then of such a solution, we can either calculate the molarity of the whole compound, we can calculate the molarity of an individual ion, or we can calculate the molarity of the total ions that are in that solution. So there's a few different possibilities there. So here we're looking for the molarity of one ion, sodium, but that's again going to still be defined as moles per liter of solution. So we need to find the moles of Na+, and then we need to find the liters of solution. Alright, so we're not given moles of Na+, we're given grams of sodium carbonate, so we have some conversions to get there. The volume is given directly as 1.28 liters, so we don't have to do any calculations for that. But we need to calculate moles of sodium plus. And again, the key idea here is that when we dissolve something in water, an ionic compound in particular, it's going to separate into ions. So we have sodium sulfate. The formula for that is Na2SO4. Sulfate is SO4 2-, sodium is Na+, and so the two of those together make sodium sulfate. And when we dissolve that in water and it separates into ions, we're going to get 2 Na+, because there's a subscript of 2 there. So this will separate into 2 sodium plus AQ and 1 SO4 minus, 2 minus AQ. So that's going to be how this would dissolve. and we're going to use this as part of our calculation for moles of sodium plus. So we should have everything we need now to calculate the moles of sodium plus. So we're starting with 12.7 grams of sodium carbonate. We're going to convert to moles of that substance using its molar mass. And so we have to get the molar mass of that. Give me a second. Should be something like 142.05. So that's the molar mass of sodium carbonate, which we're going to divide by to go from grams to moles. So grams cancel out. Now we have moles of sodium sulfate. Sorry, not carbonate, sulfate. We have moles of sodium sulfate, but we can't stop here because we're not looking for that. We're looking for the moles of Na plus that would be in there. And that's what we're going to use, again, this concept here. When we dissolve sodium sulfate, we release 2 moles of sodium plus. So it's going to be 2 moles of Na plus for every 1 mole of sodium sulfate we dissolve. Alright, so that calculation then will give us the moles of sodium plus. And that's probably the step. This last one here is probably the step that most people would have forgotten on this problem. So we get 0.179 moles of Na plus. So that goes back in here to calculate molarity. And then the molarity of that would be 0.140 or 139, depending on how you round it. Alright, so assuming I didn't mess up any of my numbers, that's going to be the series of steps that get you there. So when you're calculating moles of an individual ion in solution, you have to account for how many of that ion are in the formula and then would thus be released per mole of substance you dissolve. Alright, so that's one variation, and then the next one here uses the same concept, but we're actually not calculating molarity, we're just calculating moles. So how many total moles of ions are released when the following sample dissolves completely in water? 3.73 moles of potassium sulfate in this case. So very similar compound, potassium sulfate. Again, same argument as last time. Potassium sulfate, when it dissolves in water, it's going to make K plus and SO4 2 minus. But remember, there's 2 potassiums in the formula. So it's going to be 2 K plus and 1 SO4 minus. And this time we're looking for total moles of ions. So when an ionic compound dissolves, it's going to form positive and negative ions in the solution. So if we're looking for the total moles of ions, this is going to be a simple calculation. We have 3.73 moles of K2SO4 dissolving. And when we look at what happens, we're going to form 2 moles of positive ions, 2 moles of potassium ions, and 1 mole of sulfate ions. So that's a total of 3 moles of ions, 2 K plus, 1 SO4 minus. So there's 3 total moles of ions per mole of potassium sulfate that we dissolve. And so all we have to do is just multiply 3.73 times 3. That's all there is to it. So this one we're not calculating a molarity, we're calculating just a number of moles, which is 11.2. Alright. And so then we would often use that number then in another calculation with, volume of solution or something to make a molarity, but in this case that's where we stop. We're just looking for moles of ions. We don't have the volume of the solution, so we can't calculate molarity even if we wanted to. Okay, so that uses the same concept, but that time we're talking about total moles of ions where you have to account for both the positive and the negative ions. And then finally, the last one I'll do dealing with molarity is if you have a mixed solution. So if we have here we're looking for the molarity of F minus in a 250 milliliter solution containing 2 things, 18.34 grams of lithium fluoride and 4.32 grams of sodium fluoride. So we have 2 things being dissolved in water. So when you already dissolve 2 things in water, the total number of moles is going to just be additive for a specific substance in water. So here we're looking for a molarity of F minus. So what we need is, for the molarity of F minus, we need the moles of that ion, fluoride, divided by liters of solution. And we're told here that the volume is 250 milliliters for the total solution, so that's going to be 0.250 liters. So we have the volume already. We just have to divide milliliters by 1,000. But we have to find moles of fluoride. In this case, it's going to come from two different things, lithium fluoride and sodium fluoride. Alright, so we have to do two calculations now. So for lithium fluoride, the moles of F minus in there, we have 18.34 grams of lithium fluoride. We're going to convert to moles using its molar mass. Let me get the molar mass. It's 6. So the molar mass of that should be about 25.91. So that's moles of lithium fluoride. Now, technically speaking, there's one more conversion here because we're looking for just the moles of fluoride that are in there. In this case, it's a 1-to-1 ionic compound. So when lithium fluoride dissolves, we get 1 mole of lithium, 1 mole of fluoride. So it's just going to be 1 mole of F minus per mole of LiF. So that's a trivial conversion, but technically one that we need to do. And so what we're going to get for that is 0.708. I guess we do right sig fig 7078 moles of fluoride. So that's the piece we get from lithium fluoride, and then from sodium fluoride, which is also dissolved in the same solution. We're going to do the same calculation. It's just that we have a different mass of sodium fluoride, which is 4.32 grams, and then a different molar mass because it's going to be a different compound now. So sodium fluoride, we use its molar mass in the first step, so that's going to be 41.99. So that gives us moles of sodium fluoride. Again, there's a trivial last conversion because there's 1 mole of F minus per mole of sodium fluoride. Again, this is a 1-to-1 ionic compound. And then what we get for that is 0.103 moles of F minus. So the total moles of F minus is going to be those two things added together. 0.7087, which was the moles that we got from lithium fluoride, and then 0.103, which is the moles that we got from sodium fluoride. So those two added together is going to be 0.812. I guess 811 if we're doing rounding properly, but that's not going to cause it. Alright, that's not going to cause a problem. Alright, so that's 0.812 moles of fluoride total, so that goes up into here, divided by the volume of the solution, which is 0.25 liters. So what I got was 3.25 capital M molar. Alright, so yeah, I would need to double check my numbers, make sure I didn't mess anything up there, but assuming all the numbers are correct, those are the series of steps you're going to do. You're going to take each of those masses, convert to moles of compound and then moles of ion using the simple conversion, add them together, and divide. Alright, so that was the last question that deals with quantitative aspects of molarity. The rest of these are conceptual problems dealing with different types of aqueous reactions. So most of them that we had trouble with were redox reactions. That's probably the newest and the most unfamiliar to most of us. But there was one question here about an acid-base reaction. So we want to know which of the following is a spectator ion in the reaction between NaOH and HCl. So first let's write out the overall chemical reaction. We're going to have to split it up into ions and things to find out spectator ions. But the overall reaction, it's an acid and a base. HCl is the acid, NaOH is the base. So if we react those with each other, remember that the outcome of an acid and base reaction always is going to look very similar. You're going to have water forming from H plus and OH minus. So that's one of our products. And for these, it's going to be fairly important to write the little AQ or whatever symbol. So water forms as a liquid in the solution. It's not really thought of as an aqueous dissolved compound. And then the other product is going to be the ionic compound that's left behind with the cation from the base, sodium plus, anion from the acid, Cl minus. Those, of course, make sodium chloride and HCl. And we should recognize from solubility rules that all sodium salts are soluble, so this will remain dissolved in solution. So in this reaction, as is the case for most acid-base reactions, not all, but most of them, there is no precipitate being formed. So a lot of you picked choice E here. There are no spectator ions because there is no precipitate. Now it's true that there's no precipitate, but it doesn't mean there's no spectator ions. So precipitation reactions often and almost always do have spectator ions, but that's not the only type of reaction that has spectator ions. Pretty much any type of aqueous reaction can have spectator ions. So this one's not going to be correct because the presence or absence of a precipitate doesn't tell you whether or not there's going to be spectator ions. We still have to go through and figure out, are there any spectator ions? Are there any ions that appear as aqueous dissolved ions on both sides of the arrow? So for this, we need to separate out the reactants and the appropriate products into ions. So sodium hydroxide dissolves as Na plus and OH minus. And then HCl, which is a strong acid, separates as H plus and Cl minus. So it is important to know that this is a strong acid. Strong acids are the only ones that you would separate like this into H plus and the anion. And then on the product side, we have H2O, which is a covalent compound, so that's not going to be written in ionic form. That's going to be written as H2O. But then we still have an ionic product, sodium chloride, which will remain as Na plus and Cl minus. So in this reaction here, the ions that appear on both sides in the same form as dissolved aqueous ions are going to be Na plus and Cl minus. So OH minus and H plus combine to make water, but the rest of those ions are going to be spectators. They appear in the same form on both sides of the arrow. So which of the following is a spectator ion will be A, Na plus. Cl minus is also a spectator ion. That's not listed as one of our answer choices, but OH minus combines with H plus, so those two are not spectator ions. They form water when they combine. H3O plus is just another way of writing H plus, which you'll learn more about in Chem 2, but for our purposes it doesn't matter. Nonetheless, it's not a spectator ion in this reaction anyway. Okay, so that's how we deal with that one with spectator ions for an acid-base reaction. Now the rest of these deal with redox equations, a couple that are more conceptual and then one that does involve balancing. So an oxidizing agent in a redox reaction does what? So the terminology here is, again, a little bit strange, but we just have to remember that oxidizing agent is the species that does the oxidizing, which means itself is being reduced. So there's basically a few things for oxidizing agent. It's the one that gets reduced, and because it's getting reduced, that means it's gaining electrons. So reducing means you're gaining electrons. And the other way to identify what's being reduced is that an oxidizing agent, or whatever is getting reduced, its oxidation number is going to decrease during the reaction. So those are kind of the key essential aspects of what an oxidizing agent is. A reducing agent would be, of course, the opposite. A reducing agent gets oxidized, loses electrons, and its oxidation number increases. So here we have four choices and none of these. An oxidizing agent in a redox reagent loses electrons. Well, no, the oxidizing agent gains electrons because it's getting reduced. That one's wrong. Must contain oxygen. A lot of oxidizing agents contain oxygen, but they don't have to. Anything that gets reduced during a reaction can be an oxidizing agent. It doesn't have to have oxygen in it, so that one is false. Increases its oxidation number. Again, that's opposite. Oxidizing agent decreases its oxidation number during the reaction because it's getting reduced. D, becomes oxidized. Well, no, the oxidizing agent is one that becomes reduced. So all these are opposite. A, C, and D are all opposite of what it should be. So the correct answer for this is none of these. So it is a little bit tricky to keep straight oxidizing agent and reducing agent and what it means in the context of a redox equation to get oxidized or get reduced, but we have to keep all of that straight to be able to identify concepts like this. So as I said, on the upcoming exam, there'll be 3 questions with redox equations. One of them will be conceptual like this, something about oxidizing agents, reducing agents, or just oxidation numbers in more general terms, and then 2 of them will be balancing. So these types of concepts could come up, and you have to be able to identify the difference between oxidizing and reducing agent and what that means in terms of gaining electrons, oxidation number, and so on. So then this question requires us to sort of apply that concept. So in the following reaction, which is the oxidizing agent? So again, oxidizing agent means a few things. It's going to be the one that gets reduced, the one that gains electrons, but the easiest way to identify it is to assign oxidation numbers and look for the one where the oxidation number is going to decrease during the reaction between the reactant and the product side. So when we're identifying oxidizing or reducing agents in a chemical equation or whatever, getting oxidized or getting reduced, however the problem is worded, the most straightforward and most accurate way to do that is going to be to assign all the oxidation numbers. So in this equation here, we have copper, which is an element by itself, so it's going to have an oxidation number of 0. We'll just write them right above. So you have 0 for copper, HNO3, so we've seen this one a lot. In a covalent compound, oxygen will be -2. Hydrogen will be +1, so if you have 3 -2s and a +1, that means nitrogen must be +5, so that they all add up to 0. And then on the product side, we have copper nitrate. So for ionic compounds, the oxidation number of the metal is just its charge. So we have 2 nitrates in this formula, 2 NO3 minuses, which means the metal has to be +2. Nitrate is still NO3 minus, which is still going to have the same oxidation numbers as HNO3, -2 and +5. So a little bit of a helpful shortcut is if something is just losing H+, so here it's going from HNO3, and then here it's just NO3 minus as an ionic compound. If it just loses H+, the oxidation numbers of what's left are not going to change, so it'll still be +5 to -2. For NO, we have -2 for oxygen and +2 for nitrogen, and then for H2O we have -2 and +1 as we always do, -2 for oxygen, +1. So we're going to look for the ones that are changing. In particular, we're looking for the ones where the oxidation number decreases. So copper is going from 0 to +2, so that one is going to be increasing, so that means copper is our reducing agent, which we're not asked about here, but if we wanted to be more complete. Copper as a reducing agent is getting oxidized, going from a smaller to a larger oxidation number. But here we see that nitrogen in HNO3 is going from +5 to +2. So nitrogen is going from +5 to +2. That means that this is going to be our oxidizing agent. But the oxidizing agent is going to be the whole compound that nitrogen is part of, not just nitrogen itself, not just the atom. So even though nitrogen is the atom that's getting oxidized, the oxidizing agent is going to be the whole thing, HNO3. So in this problem, HNO3 is the oxidizing agent. Now there's some nitrogen that's also not changing its oxidation number, so HNO3 sort of serves two purposes. It supplies the nitrate counterions and it gets reduced during the reaction, so it really is doing two things. But it would be the oxidizing agent because it's the one that is getting reduced during the reaction. Oxidation number going from +5 to +2. Whenever the oxidation number is decreasing, that means the species is getting reduced. And the whole thing, HNO3, would be what's classified as the oxidizing agent. Alright, and then the next problem asks us to identify which of the following is not a redox reaction. So for these ones, again, the straightforward and surefire way to do it is going to be to assign all the oxidation numbers, which could take a while if you're dealing with 4 reactions like this. So I'll go ahead and do that, but I'll show you a shortcut a little bit later to, in this case, narrow down all of them. And so if we assign oxidation numbers for this, if it's a redox reaction, it's going to have 2 species that are changing oxidation numbers. Two changes, not something getting oxidized, something getting reduced. If it's not a redox reaction, all the oxidation numbers will be the same on the reactant and product side. So here we're going to have carbonates. This is going to be -2 for oxygen. I can't do it without the little lines. I'm too used to that. -2 for oxygen. That's 3 -2 is -6 so +4 for carbon. HSO4 minus. That's going to be hydrogen sulfates. That's going to be again -2 for oxygen, +1 for hydrogen, and that comes out to +6. We have 4 -2s is -8, +1 is -7, +6 is going to be -1, which is the total charge. Hard to see there. And then HCO3 minus, we're going to have -2 for oxygen, +1 for hydrogen. So we have 3 -2s is -6, +1 is -5. The whole thing needs to add up to -1, so it's going to be +4 for carbon. And then SO4 2 minus, we get -2, which is 4 -2 is -8, +6 for sulfur. So we have to be able to assign oxidation numbers to do this. This one is not obvious. But here we see they're all staying the same. Carbon on both sides is +4. Oxygen on both sides is -2. It appears in a few different places. Hydrogen on both sides is +1. Sulfur on both sides is +6. So none of the oxidation numbers are changing, so this one is not a redox reaction. So if we trust ourselves that we did that right, we could stop there and say that A is our answer. Now that said, it still is going to be helpful to assign the rest to be able to, convince ourselves that the rest are redox reactions. If this one is the only one that's not, the rest of them should be. So we could do that with the oxidation number approach like I just did. So we have aluminum by itself as an element is 0. H2SO4, we had similar one above, so it's going to be +1, -2, and +6. So I'll go through these quickly. H2, an element, neutral element, no other atoms in the formula, so that's going to be 0. And then aluminum sulfate, this is an ionic compound where we're going to still have sulfate as +6 and -2 for oxygen. 3 sulfates is -6, 2 aluminums. In any aluminum ionic compound, it should be +3. So here we do have changing oxidation numbers. We have aluminum going from 0 to +3, hydrogen going from +1 to 0. So this one is a redox reaction. And then the decomposition of water into hydrogen and oxygen, water is +1 and -2. And then we have 2 elements by themselves that are going to be 0 oxidation numbers. So again, hydrogen is changing +1 to 0, oxygen is changing -2 to 0, so that one is redox. And then this one here, we have sodium iodide, Br2, and then sodium bromide in I2. This is what's called a single exchange reaction. So you have +1 and -1. These are ionic compounds, so the oxidation numbers are just the charges. A neutral element, so that has to be 0. And then another ionic compound, which is +1 and -1. And another neutral element, which is 0. So again, we have all oxidation numbers changing for iodine and bromine. Iodine -1 to 0. Bromine 0 to -1. So this is also redox. So all the rest of these are redox reactions. Now, if you didn't want to go through and assign all of the oxidation numbers, because that takes some time, a shortcut that I talked about in class is that if an equation involves a pure element as one of the reactants or products, meaning an element with no charge, no other atoms in the formula for that substance, that has to be a redox reaction, because neutral elements are the only time when you're going to have a 0 oxidation number. So if a neutral element is involved in a chemical equation, if it's 0 on one side of the equation, that element has to be something else on the other side of the equation, because that's the only time that you're going to have, in our case anyway, a 0 oxidation number. So if we look at B, C, and D, we have aluminum and hydrogen involved in this one. So we have 2 elements involved, so that has to be a redox reaction. Choice C, 2 elements involved, H2 and O2, has to be a redox reaction, because that's the only time when we'll have 0 oxidation numbers. Choice D, 2 elements involved, Br2, I2, has to be a redox reaction. Now choice A does not have any elements. That doesn't mean that it's not a redox reaction. There are plenty of redox reactions that don't involve elements, so we have to still analyze that one to make sure it's not a redox reaction. But we could have quickly eliminated B, C, and D because all 3 of these involve elements, which means they have to be redox reactions. So that's going to be a helpful shortcut for identifying redox reactions, where it won't tell you in all cases whether or not it's a redox reaction, but if it has elements involved, then it has to be a redox reaction, and you don't have to do any further analysis like I did here. Alright, and then the last one here deals with balancing a redox reaction. I think we did pretty well on this for the most part, but this one gave us a little bit of trouble, and it is good to review it because there are going to be 2 homework questions on this topic, 2 exam questions on this topic. So if we go through this, we have to assign oxidation numbers first, and there's no elements here, so it's not obvious that it's a redox reaction, but we're telling you that it is, and we'll see that it is once we get the oxidation numbers. So per manganate, we have -2 for oxygen, 4 minus 2 is -8. The total has to be -1 for the overall charge, so that's going to be +7 for manganese. HSO3 minus, I think we just did this on one of the previous ones or something similar to this. We have -2 for oxygen, +1 for hydrogen. So 3 minus 2s is -6, +1 is -5. They have to add up to be -1, so that has to be +4. So we have +4 for sulfur. And then H plus ion by itself, the oxidation number is just the charge, which is +1. And then on the product side, we have an ion by itself again, so the oxidation number is just the charge +2. Sulfate, we have this time -2 for oxygen, that's 4 minus 2 is -8. The sum has to be -2 for the overall charge, so that's going to be +6 for sulfur. And then our old friend water, +1 and -2. All right, so to balance a redox equation, we start with the substances that have changing oxidation numbers. So manganese is going from +7 to +2, so that's changing, and then sulfur is going from +4 to +6, so that's also changing. And then we have to count how many electrons they're changing by. So manganese is going from +7 to +2, that's 5 electrons. Technically it's gaining 5 electrons because it's being reduced. It's serving as the oxidizing agent. But the important thing for balancing is how many electrons. That's just the difference in oxidation number. +5 to +2 is a difference of 5. And then we have +4 to +6 is a difference of 2 electrons because we're changing the oxidation number by 2. So the number of electrons in a redox equation needs to be balanced. However many electrons are lost by one substance need to be gained by the other, and vice versa. So what we'll have is, we want to make these two the same, we need to find small factors to multiply those by. The least common multiple of 5 and 2 is 10, so we're going to double this to make it 10 total electrons. And so to do that, we put a coefficient of 2 in front of both of those. And then this one we're going to multiply by 5 to also make it 10 electrons being lost. And so we need to have a 5 there and a 5 there. So that sets the coefficients for those two substances. And here we're just looking for the coefficient for hydrogen sulfite. So we can stop there because we're not going to adjust this one anymore now that we've balanced the electrons. That's going to be 5. So that's going to be our answer. Now if we want to finish balancing this, we have to look at oxygen and H+. So here we have 5 sulfites that are... So let's look at oxygen first. We have 2 times 4 is 8, plus 15. We have 23 oxygens on this side. And on this side we have 5 times 4 is 20. So we're going to have 3 waters. And then if we have 3 waters, we need to have how many H pluses? Well, we have 6 over here. We already have 5 from there, so it's just going to be 1 H plus. So that should be balanced like that. I'd have to double check oxygen and H plus to make sure I didn't mess anything up there, but it should be 23 oxygens on each side. 5 times 4 plus 3, 6 H pluses. So I think we're good. But again, for this one, we're just asking for this coefficient here. So once we set that, because that's involved in the electron transfer process, that's the one that's being oxidized in this case, we could just stop there and say that the coefficient is 5. We don't have to continue all the way out to the end. Alright, so that's going to be the last problem I think I did. Yes, so we're done. So if there's any other questions on Chapter 6, I did send an email about my office hours this week, which are going to be a little bit extended because of the exam. So please get in touch with me either by email or in person in my office if you have any remaining questions on this assignment or anything related to the upcoming exam. Alright, best wishes for your exam this week, and I'll see you guys in class tomorrow.